Howdy ho, Muso here. Let's talk about conservation of momentum. Yeah, I've got a lot of stuff going on over here. Trying not to let it distract you too much. We're going to talk about all this stuff after. Let's talk about the stuff in the boxes here. So it turns out in a closed system, it's important to recognize what we mean by that. A closed system, that's a scenario in which mass cannot enter or leave the system. It stays right within it. We have certain thing that really is kind of a law. So we've heard about the conservation of energy. That means the total amount of energy in the beginning must be present at the end, or energy is always conserved. It can't be created or destroyed. It can only change form. Turns out there's this law called conservation of momentum as well. And it's equally true and equally valid and equally important in physics. In fact, some of the most breakthrough concepts in physics take place by analyzing the conservation of momentum of really tiny particles. It's really prevalent in quantum physics right now, mechanics. We're dealing with analyzing momentum exchange between really, really tiny guys. I'm not going to get into that stuff, but understand conservation of momentum is one of those laws in the universe that really dictate all of physics and helps us understand and determine new physics. Let's just break it down though into an AP level. When two objects interact, the total sum of their momenta before the interaction must be equal to the sum of their momenta after the interaction. That means if we were to take every single object's momentum before any sort of collision takes place and add up their momentum, that's to be the same value of all of the momentum after the collision. Really important to understand the difference between those two things. Total momentum before must equal the total momentum after, or P before equals P after. One way we write that is just P equals P prime, because that prime doesn't mean it's a second object. It means it's the same object after something has happened. So we usually say P is before the collision and P prime is after the collision. Again, before I talk about this, we do need to talk about how there are two main types of collisions in all of the collisions in this world. There are elastic collisions and inelastic collisions. An elastic collision is one in which not only is momentum conserved, but so is kinetic energy, or energy in general. Basically, that means the total momentum before the collision and the total energy before the collision must be present at the end. In elastic collisions, we will have energy loss, or it's not conserved. So that would mean the total momentum before the collision and the total energy before collision, they're not all going to be equal at the end. So the momentum before will equal the momentum at the end because momentum is always conserved in a closed system. However, the energy in the beginning likely won't be conserved at the end if it's inelastic. Typically, there are two equations that fall through with this, and it's really the same equation. I'm going to explain the difference, but before I do that, how do we determine if we have an elastic collision? Well, if the problem that you're dealing with says there's no energy lost in the environment or there's no energy loss in general, it's a good indicator it's elastic. Couple other things though you can pay attention to. Typically, the total number of objects before the collision will be equal to the total number of objects afterwards. For example, this box hitting this box up here is an elastic collision, likely at least. We have two objects that have momentum before the collision. Let's wait for it. Good. And then they're going to collide. And how many do we have left afterwards? We still have two. Whereas an inelastic collision, we typically have a difference in numbers. We either have more in the beginning than we had at the end, or we have more at the end than we had in the beginning. Think of this fish swallowing up this other fish. There are two objects in the beginning. Oh, there it is, and only one at the end. That's nature, folks. That's an inelastic collision. That basically means energy was used in consuming that fish. Some other indicators of inelastic collisions, if we have crunching or loud sounds or fire or we have glass breaking or denting, all of that means energy was being used. Think about two cars hitting each other. If those two cars hit each other and then crunch and then deflect off of each other, we'll still have two cars in the beginning and we'll have two cars at the end. But that crunching and that jamming up, all that metal bending and all that stuff breaking, that was using energy, so it's likely an inelastic collision. But then if we think on the flip side, if we have bumper cars, two cars bouncing off of each other, we have two in the beginning, we have two at the end, but nothing was used. There was no energy used. There was no crunching. There was no breaking. There was no loud sounds. So energy is conserved. I will tell you, all real life collisions, with the exception of a few ideal scenarios like ideal gases, all real life collisions will always be inelastic. There is always some level of energy lost during a collision. However, the majority of problems in which we're going to analyze in this class are likely going to be elastic collisions because they're considered to be ideal models. So we want to understand what happens ideally if there was no energy loss. Just recognize in real life there likely is. So, because we have two objects before and two objects after, or three objects before and three objects after, or four before and four after, whatever, we're usually going to be able to say the momentum of each object in the beginning must be equal to the total sum momentum of each object after the collision. So this is how we set up elastic collisions. If I had three, I'd say m1 plus or m1v1 plus m2v2 plus m3v3. We have to add up each individual momentum. And by the way, some of these objects might not have momentum in the beginning, but we're still going to consider them as objects. And then we're going to set it to equal to that same object, but now we're going to write m1 v1 prime. This means it's the first object, but after it's been collided. m2 v2 prime. It's that second object, but after there's been a collision. So we would use this setup to analyze the momentum of these two boxes up here. If I knew the original velocity and the mass, and then they bounced, and I knew their new velocities, or let's say I knew one new velocity, I can set up that ratio and find the new velocity of the other object. And I'll go through an example problem shortly on this. Okay, in inelastic collision, we're going to say the total momentum in the beginning must equal the total momentum at the end. That's still true, but now we have something here happening. We have two objects in the beginning, so we'll say m1 v1 plus m2 v2. But after the collision, it actually is more or less one object. But that total mass is still need to be accounted for. That fish swallowing the little fish, that little fish is just inside here, so the big fish gained mass. So now we're going to add the two masses together, treat it as one unit, and then that'll be its new velocity prime. I'm going to go through some numerical examples to talk about that. Last thing I want to talk about, well, maybe not the last thing, but the next thing I want to talk about is this little guy jumping up and down here. And my question to you is this ball, when it hits that ground, is it an elastic collision with the ground, or is it inelastic? You should be able to tell just by looking at it. Well, if it was elastic, then all of the energy would be conserved, which means if it started up here, hits the ground, it's going to fire back up with the original energy it gained, and it's going to eventually stop at the same original PE. So if the ball returned to its original height, no energy would be lost on that impact with the ground. Therefore, it would be elastic. However, because it's not reaching its original height, we know energy is being consumed. And that energy is being consumed either with the air that it's traveling through, or more likely, or maybe even both, the impact itself. It's losing energy to the environment, leaving the system. Okay? Let's go through some example problems on this. Actually, you know what? Now I think about it, I'm going to save that for another video because that might take a long time. I'm going to close up this video now, and then I'm going to do some examples on conservation of momentum. Again, recognize P before must equal P after. We always have to set the original part on one side and the new part on the other side, and we're going to set those two terms equal to each other. Let's go through a set of examples in the next video. Thank you.